Welcome to the first video. What we're going to be doing in this video is looking at functions and defining what a function is and identifying whether a relation is a function or not. So the title of this video, 2.1, is the section in your book, and we're going to call it Represent Relations and Functions. All right, so the definition of a function is a relation in which each input has exactly one output. I'm going to go ahead and underline the words exactly one, making that the most important part of the definition. So I think a good way, and this is not a way that I came up with, but a good way to think of what a function is actually using an illustration of a pop machine. All right, so in my pop machine, I'm going to have several different buttons, and these buttons obviously represent the type of soda or drink that you're going to get when you press the button. All right, so my machine, the first button is going to give me Coke. The second machine is going to give me Dr. Pepper. Third, we'll do Mountain Dew. Fourth, I think most of you guys are aware that sometimes a machine will have different buttons for the same pop. So we'll do another Dr. Pepper. The fifth one we'll do water, I guess, just to mix it up a little bit. And the sixth, we will do the most disgusting drink ever, which would be Diet. All right, so basically the way a pop machine works is you walk up to it, you put your money in, you hit the button, and you get out the pop. So let's look at an example of something that is a functioning machine. All right, so input, output. So let's say we go to the machine, we hit the number 3, and what we get out is a Mountain Dew. Next input, we go to the machine, someone else goes up to it, let's say, and hits the number 4, and they get their Dr. Pepper. Next person goes up and hits the number 2 and gets a Dr. Pepper. Now again, that's still a machine that's functioning. Even though I hit different buttons here, I know I get the same outputs, but these are different inputs. So going back up to my definition, each input has exactly one output. So this is okay to see this where you have a repeating output. And then someone hits the next one is number 5, and they hit water. So what I'm going to write down here as my conclusion is this is a function. Each input has exactly one output. So a lot of times in this video or in the worksheet that you guys are going to do, it'll ask you, is it a function, yes or no, and then it'll ask you to explain. When you explain, if it is a function, you'll just simply say each input has exactly one output. All right, so now I want to look at one that is not a function. All right, so in this relation, the first person gets hits a 1, gets a Coke. So okay so far. The second person goes up, hits a number 2, gets a Dr. Pepper. Still good there. The next person goes up, hits the 1, expects to get a Coke, which that would mean the machine is working, but instead gets the dreaded death Diet. So if you notice, what happens here is I have a machine that's obviously busted. I'm hitting something and it's giving me two different things. Well, that's obviously not good. So what I have is I have the same inputs, but I have different outputs with that same input. So when an input repeats, the only time it would be a function is if you get the same output. Since we have different outputs here, this is not a function. So I'm going to say over here, this relation is not a function. And instead of just saying each input does not have exactly one output, I'm going to be really specific here, and I'm going to talk about which input that is. So I'm going to say input 1 has two different outputs. And that makes it a not functioning machine. All right, so next what I want to do is look at just some, let's take the pop machine example out of it. We can go back to that and kind of reference that as we need to. But let's look at some just examples of, notice so far what we've done is tables. So we're going to do the same thing. I'm going to ask basically, is it a function or not? But now we're just going to strip things away and just use the variables x and y. Go ahead and copy that down. All right, so now if I'm looking at this table, what I would ask you to do is think through whether you believe this is or is not a function. So in looking at this, is it or is it not a function, a lot of students would say, well, no, it's not, because you have two outputs that are the same here. But if I go back to my original where this was a function, notice that you are allowed to have the same output with different inputs. What you can't have for a function is the same input and different outputs. So notice that each input here is different. Outputs can repeat, so that part is okay. So this is actually not a function. Oh, I'm sorry, I'm writing the wrong thing. This is a function. My bad. So this is a function. Each input has exactly one output. All right, let's look at a second example. Make my table vertical this time. All right, so we'll do 2, 5, 3, 7, 14, negative 1, 2, 6. So again, just in copying that table down and looking at my answer, or in thinking about what my answer would be here, is this a function or not? Yes or no? Hopefully we said no, it's not. And if you notice right here, I have the input 2 and the output 5, the input 2 and the output 6. So because these two are different, this makes this not a function. And so what I'll say here specifically, the reason that it's not is because the input 2 has two different outputs. All right, so those first two examples were with tables. That is one way that we can write a relation. Another way to write a relation is just a set of points. So third example here, we'll use a set of points. So that set of points is going to be 1, 0, 2, 0, and 3, 0. Now when I write a set of points, in order for me to show that these 3 points represent a relation, I'm actually going to put on the outside braces. And those braces, again, just that's the notation that we use whenever we have a relation that is a set of points. So again, the question is this thing a function or not? So just in thinking through, is it or not, does each input have exactly one output? Well, I have 3 distinct inputs here. Even though the outputs repeat, that's okay. So I'm going to say, yes, this is a function. And again, I want to explain why each one is. And for this, since it is, each input has exactly one output. So that's a second way that you can represent a relation. A third way to represent a relation would be something called a mapping. So it's similar to a table. So there's my inputs and outputs. And then in order to know which input goes with which output, what I actually use is arrows. All right, so right there is my map, or mapping. So again, the question is this a function or not? So if I look at the input 3, it goes to 5, and it also goes to 6. Well, that's the same input with two different outputs. Well, that means that this is not a function. So specifically, it's because the input 3 has two different outputs. I'll do one more of those, another mapping. I want to remind you to feel free to pause the video if at any point I'm going faster than you can write, if you are taking notes. All right, so if I look at the input and the output here, so 3 goes to 6, 1 goes to -10, 3 goes to 6, and 2 goes to 5. Notice that I have an input that actually repeats, but it goes to the same output, so I am okay there. So because of that, each input does have exactly one output, and so this is a function. All right, so we've looked at 3 different ways to represent a function. We've looked at tables. In example 3, we saw a set of points, and we saw mapping for these two. So the last way would be to write it as a graph. So the graph, I notice I don't have graph paper here. Likely you don't have graph paper either. These are just going to be rough sketches of a graph. So let me do it in terms of a couple points. So we'll do the points -2, 0. And then I'll do the point 5, 4, so approximately right there. The point 7, 8. And then the point 5, 6. So just in looking at this graph, what you should be able to recognize right away is that I have the same input with 2 different outputs. And so right away I should be able to hopefully see that this is not a function. The input 5 has 2 different outputs. Now, there's another way to tell from a graph if a relation is a function, and that is something called the vertical line test. Hopefully you remember something from that from Algebra 1. So the vertical line test essentially says this. If I can draw a vertical line anywhere on this graph, and it does not touch more than one point at a time, then it passes the vertical line test, which means the relation is a function. However, if I can draw a vertical line through more than one point, then that means the relation is not a function. And so if I look at these 2 points, 5, 6, and 5, 4, if I draw a vertical line through those, notice that it touches both of them. Here I'm okay because it only touches 1 point, but here specifically it touches those 2 points. And so visually, what you'll see when a relation is not a function is that they are stacked on top of each other. If I go back to any of these other examples that were not functions, so example 4 was not a function, example 2 was not a function, all of those, if I were to graph those, you would see that they are stacked on top of each other. Same input, different output, and so it does not pass the vertical line test. So the way that we've said this before is, when we say, why is it not a function? Well, specifically, the input 5 has 2 different outputs. For a graph specifically, another way that you could say why it's not or it is a function is you can refer to the vertical line test. So what I'm going to say here is, this is not a function. The input 5 has 2 different outputs. Or, instead of saying that, what I could say is, does not pass the vertical line test. Now, on my piece of paper, I'm going to turn my piece of paper sideways just to save some paper, and let me just write down really quickly for us a definition of the vertical line test. I don't think this is the official book, Google, interwebs definition. This might be the Mr. Salter's definition, but it serves its purpose. So here it is. If any vertical line passes through two or more points, the relation is not a function. If any vertical line passes through 2 or more points, the relation is not a function. And so that's what we're seeing here in this last one. All right, so another example. So if I had a graph that looked like this. Question is it a function or not? In other words, can I pass a vertical line through more than one point on any point of this graph? And really quickly you see that, well, yeah, this doesn't exactly work out. So, for example, I could draw a vertical line here or here or here. Really anywhere on this graph, it's going to hit more than 1 point. And so what I'm going to say is, this is not a function. It does not pass the vertical line test. Take a look at one more of those examples. So when I look at this one, anywhere that I draw a vertical line is going to pass through only 1 point on this graph. And so what I can say is, this is a function, and I can say that it passes the vertical line test. Now you are allowed to say that each input has exactly one output. You can still say that. Usually for a graph, though, we will use this idea of the vertical line test more so than each input has exactly one output. What I don't want you guys to say, for example, number 5 is, yes, it passes the vertical line test. Okay, well, there's no line here visually drawn. So make sure for those other types where you have a mapping or you have a set of points or you have a table, make sure that you're talking about each input having one output. For a graph, though, you can talk about the vertical line test. All right, so that's it for functions. Now we're going to move on to 2.2, which is to find slope and rate of change. Now this definitely is review from Algebra 1, and so I don't want to insult your intelligence, but for those of you guys that might need a quick refresher, let's just go ahead and define what slope is. So there's several ways that you can define slope. So the official definition is, it is the ratio of the vertical change to horizontal change. And hopefully you guys know I'm talking about a graph. Vertical change to horizontal change. So in Algebra 1, there were several different ways that we kind of talked about and defined what slope was. So I want to list those out right now. So one way we define it as just rate of change. So whatever the rate of change is your slope. So another way to say that is if we look at vertical change to horizontal change, I'm going to say the change in the dependent variable over the change in the independent variable. So I have two things I need to discuss here. First of all, you might ask, why the heck am I drawing a triangle? So that triangle is the Greek letter delta, and anytime in math you see a triangle like that, generally outside of geometry, what it's talking about is change. So what this is saying is the change in the dependent variable. Well, if I think about an xy axis, the dependent variable is my y, and the independent variable is my x. So vertical change would be y, dependent, over horizontal change would be independent. So another way I could say this is the change in y over the change in x. Now when I think about change in math, generally change means, well, subtraction. If I go from one to the other, I subtract off. So y2 minus y1 over x2 minus x1, which is that nice, neat formula that so many of you have memorized and perhaps forgotten until right now. Or another way you can define slope, which is very basic but very useful, is to just say it's rise over run. All right, so there's a bunch of different ways to define slope. So now let's go ahead and work through a few examples together for how to find slope. So let's start with the table. So go ahead and copy that down, pause if you need to. So when I'm looking at the slope of this table, what a lot of students make the mistake of doing is they just look in the change in y. So they'll say, oh, well, it's going up 2, so the change is 2, so the slope must be 2. And they forget, what about x? Because x doesn't always go up by 1, and in this case it doesn't. So here we can see each time we're just adding 2. But if I look at the change in y every time, we're actually adding 3. Okay, so going back to Algebra 1, hopefully we recognize that means this is a linear function because it does have the same rate of change. But when I'm looking at what the slope is, the slope specifically, and if you remember from Algebra 1, a lot of times m will represent slope. So the slope is the change in y over the change in x. No, you don't have to write that down all the time. Just for your notes, I'm writing that down. So the slope would be 2/3. I do want you guys to write these as fractions and not decimals, especially for something like 2/3, which is 0.6 repeating. 2/3 is just much cleaner, so let's try to stay away from decimals when we're talking about what the slope is. All right, second example, what if I give 2 points? So I have a couple different ways I could do this. I could go to this nice formula that we do. I could take this and put it in the form of a table and then find the slope that way. Either way really works. You could also graph them and then look at rise over run. That to me seems like a little bit more work than you need to. But let me go ahead and use this formula. So y2 minus y1 over x2 minus x1. So what I get is 0 over 6. And so the question is, what the heck is 0 over 6? Because some of you, I'm sure, have forgotten at this point. 0 over 6 is not undefined. It is 0. So the slope here is 0. All right, so third example, I'm going to draw a sketch of a graph. So again, just a sketch, so let's go ahead and put the point 0, -1 on there. 1, -4, -1, 2, and -2, 5. So if you notice, I should be creating, hopefully, a pretty straight line here in my drawing. Okay, so I have several ways I can find the slope of this line. One way would be to just look at rise over run. So I could simply pick 2 points. I could count my rise, I could count my run, divide, go from there. I could pick 2 specific points and do y2 minus y1 over x2 minus x1. I could also take these points and put them into a table like number 1, and I could go through and do that as well. So personally for me, whenever I have a graph, it's always easiest for me to just do rise over run. So if I'm counting from 1, -4 to 0, -1, for example, I'm rising 1, 2, 3, and running 1 to the left. So that's 3 over 1. However, since I'm going to the left here, that 1 should be negative. And so when I say my slope is 3 over -1 simplifies to just -3. Now I made a comment in number 1 about how I want answers written as fractions. However, the only exception to that is when you have a whole number, or a integer in this case. You can go ahead and simplify that to -3. Please don't leave it as 3 over -1. That's a little algebra 1 type. We are stepping up our game a little bit here. Let's make sure that we write it as a whole number when it is in fact a whole number. All right, so next, what I want you guys to do is, if you have access to your book, I actually want to look at a problem from your book, and that is on page 85. And the problem number that we're going to look at together is number 5. So go ahead and pause your video, either pull up your book online, or pull out your hard copy of your book and look at page 85, number 5. So in looking at this problem that talks about forestry, I guess, and specifically talking about just trees and how often how they grow and everything. So what we're looking at is, in 1965 there was a tree with 137 inches, in 2005 a tree with 141 inches. We want to find the rate of change. So in other words, rate of change is obviously the slope. So when I'm finding the rate of change, where students often get confused with this is what variable goes in the numerator and what variable goes in the denominator. And so for me, I always go back to this idea of, in a story problem, in a word problem, what is the independent variable and what is the dependent variable? And if I can identify those, then I know the dependent is always in the numerator and the independent is in the denominator. So just in looking at this problem, if I just say what are the variables, well, the 2 variables must be time, because I'm going in years, 65 to 2005, and then the number of inches. Okay? So when I think about which one is the independent versus dependent, time is almost always independent. Okay? So we almost, and I'm saying almost because there are times where it's not, but almost always time is independent because we rely on time. And so when I'm looking at the change in the independent variable and the change in the dependent variable, in this case, the dependent variable is going to be the change in inches, or the change in the diameter of the tree. And then the independent variable is time, so I'm going to say it's the change in time or the change in years. Now again, remember that change is always going to be subtraction, so I'm going to subtract off. So for these, I always start where you end and I work my way backwards. So the last part that it ended in 2005, and it ended with 141 inches. So 141 inches minus 137 inches. Again, ending in 2005, beginning in 1965. So I'm just going to go ahead and subtract those. So here what I get is 4 inches, and here what I get is 40 years. Now if I simplify this, 4 over 40, and I just divide that out, really what I get is 1 inch in 10 years. Now generally, when we say a rate of change, we don't really say, well, how much did it grow in 10 years? Generally what we'll say is, well, how much did it grow in 1 year? So if I just say 1 over 10, well, 1 over 10 is really 0.1. So I would say 0.1 inches, or 1/10 of an inch, every year. Oops. There we go. Okay, so either 0.1 of an inch every year or 1/10 of an inch per year. If that explanation wasn't really that good to you, you can go ahead and take a look in your book, and maybe you were kind of doing this as I was doing this problem. It did have a step-by-step kind of instructions for how to find the rate of change. There was a second part of this problem that talked about predict the sequoia's diameter in 2065. I'm not really worried about that at this point, so I'm gonna go ahead and move on. So the last thing I want to talk about in this video is parallel and perpendicular lines. All right, so when we talk about parallel lines, now specifically from geometry, you might remember parallel lines are lines that are coplanar that never intersect. When we talk about what does that mean in a coordinate plane, in other words, if I were to graph two parallel lines in an xy axis, what would I see in terms of their equations? And so what we notice right away is that parallel lines have the same slope. But there is something that they have that is different. If they have the same slope, but they're on top of each other, then they're the same line, which means they're not parallel. However, if they are parallel lines, then they have the same slopes, but they also have different y-intercepts. So we must say both of those things. For perpendicular lines, maybe you remember, maybe you don't from Algebra 1, but perpendicular lines have opposite reciprocal slopes. Now, what frustrates me to no end is that students will always get these two things mixed up and think that they are the same word. Opposite essentially is the same number but a different sign. 5 and -5, 10 and -10, x and -x. Those are opposites. Reciprocal is when I take a number and I flip the numerator and denominator. So these are two different things. So I want us to make sure that we understand there are two different things going on with perpendicular lines. Opposite and reciprocal are not the same thing. They are different, but we put them together for two lines that are perpendicular. And specifically, I'm talking about their slopes. All right, so for example, I'm only going to do one example with us. And the question is, are the lines parallel, perpendicular, or neither of those? And hopefully you remember these symbols from geometry. I'm assuming we do. All right, so the first line passes through the points -2, 8, and 2, -4. And the second line passes through the points -5, 1, and -2, 2. All right, so go ahead and pause the video. And I would suggest go ahead and find the slope of each one of those and then try to figure out what type of lines you have here. Are they parallel, perpendicular, or neither? And pause the video, and then when you come back, I'll go ahead and work through it. All right, so I'm going to find the slope of each one of these. Hopefully you've already done this at this point. Okay, slope of line 1. Sorry about that. So I'm going to do y2 minus y1 over x2 minus x1. So careful when you have minus and negative, you change that to a plus. Slope of the second line. So when I look at these, I can see that these are opposites. One is negative and one is positive, and they are reciprocals. 3 and 1/3 are reciprocals of each other, which means that these are perpendicular. And I'm just going to give a very quick explanation and just say these are opposites, reciprocal slopes. Now, if you found that these had the same slopes, you couldn't just say right away that they are parallel because remember they have to have different y-intercepts. So what you would do for that is you would find the y-intercept of each one of those lines. If you can't remember how to do that, that's actually coming up in a lesson in the future. So if at any point you need to go back or needed to go back to revisit any of these points, feel free to do so. See you in class.